So, this Intel instability thing has been several months. Well, actually, it's been over a year. But we've got new microcode and new motherboard defaults. What's the score? How are things looking? I've had over 20 processors mailed to me from all over the world. What's the post-mortem on this project? I've had time to go over the data. Well, data that I've gathered, but also I've made some new friends, field service technicians, other computer janitors, and they've brought a lot of data of their own. And no one likes hard data more than I do, but the problem is looking to have equal parts technical and political. Without opinion and intrigue, it's not really super interesting. Nobody will watch. So I'm going to heap on lots of intrigue and opinion and everything else. I think there's more here yet to discover, in fact. And I'm sure that the microcode 0x129 that we have is definitely not final. Come with me, let's take a closer, deeper look. Is he hamming it up? It's like, well, yeah, because otherwise I would go blind from looking at the spreadsheets. If you're just joining us, you should check out my earlier video. As I said, there were lots of signs that something wasn't right with Intel 13th gen CPUs, maybe 6 months after the 13th gen launched. But it took until almost a year after 14th gen launched to get any action from Intel. I mean, publicly, up till a few months ago, the word from Intel was a deafening, oh. Behind closed doors, Intel workers, the wise and reasonable graybeard knowledge workers, kindred computer janitors like me, both in and out of Intel, were sounding the alarm that they were facing strange stability issues that would come to be known as degradation and partly referred to by Intel as vmin shift. Yeah. A lot of 13th and 14th gen problems. There was and is a lot of finger pointing to motherboard manufacturers, and I think there's a lot to that. I think motherboard manufacturers have got off scot-free, but the problems in Intel's own microcode were more serious than they let on, and I'll show you why. Oh Lord, he coming with the data! So, for data, for the first video I did, which included 2 large data sets with 2 types of data, game crash telemetry from game crash databases, and customer support tickets from a data center selling access to i7 and i9 systems primarily to host game servers. Many folks have since reached out from that video to connect, and so I've been able to connect with others and other computer janitors and in my kind of a role and expand the data center. And those are my people. That's my agenda, is to make the computer janitor suffering less and the graybeard suffering less. And I've observed some really interesting stuff from this data. And I just want to be clear that the conclusions that I'm drawing, they might be wrong, and they might be based on my own flawed understanding of what this data is telling me. I had to sort of put together some of my own tools to gather some of this telemetry. You can check out that video as well. That's a fun one on the Linux channel. But as for data and what I'm looking at from data centers and game hosts, well, game hosts that maybe probably don't rise to the level of a label of data center. Keep in mind, sometimes your Minecraft server that you're renting might be a 13700T based small form factor Lenovo or Dell or HP. A small form factor business class machine with potato class VRM and cooling just hanging about on a wire shelf in a warehouse in Hoboken. You never know. So the first thing I noticed is that sometimes you could maybe call this situation gaming CPUs that can't game. Like the i7 and the i9, if you ask them to game too much, bad things happen. I've noticed that in the data, it seems like the CPU degrades faster when it's doing gaming versus, say, cryptocurrency mining. How do we know? Well, for one population of 862 systems that have an i7 or an i9 CPU of any variant, 13th or 14th generation only, 42 of those systems were released by one customer doing something like cryptocurrency mining. We know from the power usage and from talking to them that this population of systems has been running a consistent power load 24/7 basically for the better part of 2 years. And these systems weren't all leased at the same time. Some systems that had been leased were released back into the population of systems available for lease. But most of these go back to mid-2023 or early 2023. Mostly these systems have been with one customer that whole time, though, and they've experienced a grand total of 3 failures where the ticket resolution was ultimately replace the CPU. That's about 7%. But the sample size is low. And what's curious about that is that 7% is a relatively low failure rate versus machines we know are running game servers. Whereas for anything other than an i7 or an i9, that's an absurdly high failure rate. This kind of led me down a path to trying to investigate if you were going to experience a failure, is it workload related? And remember, these gaming systems were configured conservatively, without overclocking, without using much power, and we can demonstrably show that they weren't using as much power as their cryptocurrency counterparts. In fact, the power curve usage for these systems looked a little bit like a sine wave. More players would log on during the day, they would drop off at night, and again, I mean, makes sense, right? Gamers gotta sleep too. I mean, you can only do so many 20-hour gaming sessions before you're just completely pooped. And that's exactly what we'd expect to see power-wise, and yet this population was at least twice as likely, maybe 3 times as likely, to get a trouble ticket related to some sort of CPU problem. A problem that might go away, locking the multiplier to a maximum of 53, or setting a fixed voltage for the processor on the order of 1.2 or 1.3 volts. But this is kind of the lazy way to deal with it, that only a sad person who has no desire to learn more about the nature of the problem would actually deal with it. So I decided to try to separate the systems that had better cooling from the ones that had worse, and what I found there was really interesting. For systems that had copper tower coolers, basically, a 10 or 15,000 RPM fan, 2U, standard issue rack mount server, those seem to develop problems less often than the ones that had the over-the-top liquid cooling. The ones with liquid cooling were more likely to develop problems. And this is where I began to suspect thermal velocity boost. This seems to mainly affect the i9 CPUs, and it made me think that we might be looking at a combination of issues. If the CPU is cool, it will try to boost more. Does it try to boost to the point of ruination? Does it ask for more voltage because it is being cooled so aggressively? I suspect that is true, or at least that was true before the 0x129 microcode, but I think there's probably more to uncover there. Not only that, but it seems like Intel changed how the thermal velocity boost stuff worked, including thermal reporting, around the end of 2023. That was a year ago at the time that I'm making this video. That was a long time. It was a long time to be silent on an issue. I also looked more into the gaming workloads and the voltages requested by the processor during gaming workloads. The boost algorithm doesn't seem particularly smart on Intel's part. And here's a really interesting thing I was able to unpack by looking at the code sort of point blank inside of GDB and looking at there's performance counters and things like that in the processor. It looks to me like when you're dealing with netcode and something that's poorly optimized, like say Minecraft, the boost algorithm is looking at its own pipeline, and it's looking at the state of the machine, and it says, hey, I can boost. But the problem is it can't actually boost. What it needs is a clear instruction queue. There doesn't need to be any bubbles in the instruction pipeline, and it needs everything to already be in cache. But it's not. It's in memory, and so we're waiting on memory, and memory is glacial when we're talking about 5 to 6 billion cycles per second that the processor operates on. I mean, on a billionth of a second time scale, from the perspective of a CPU, it has been waiting days or weeks for more voltage since it asked for more voltage. If the CPU has work to do, the load will pull the voltage down. So if the CPU doesn't really experience the elevated voltage, if it's actually got stuff to do. This isn't a lot different than when the lights dim when you turn on your vacuum cleaner. So if the CPU is stalled and uses more power, then effectively it doesn't actually see the increased voltage because it's doing something. If the power company could send you a little more power at just the moment the vacuum cleaner comes on, you won't notice the lights dim. There's no droop. There's machinery on the motherboard designed to deal with that kind of thing when we're talking about CPUs and CPU billionths of a second timescales. If the CPU is hot, however, it won't try to boost, or at least it won't try to boost as much. I suspect this finding for W680 and data center configurations will also hold true for gamers and gaming motherboards. So gamers who have tower cooling will probably have a greater chance of not having had issues versus their AIO and liquid cooler counterparts. Unfortunately for these commercial folks back in the data center, a lot of their systems they splurged on to get really killer liquid cooling for their gaming server fleet. And I think that contributed a lot to the degradation in the end, probably because of the boost algorithm. I also think that this is kind of workload related, and so bursty netcode and code that is going to create a lot of pipeline bubbles or cache misses is probably not covered well in Intel's internal test suite. If you have a degraded CPU, unless it's severely degraded, it will not fail at Y-Cruncher or other stress tests. You can leave it running forever. Intel is no doubt testing for all of that. Even Intel's own stress test tool with their overclocking utilities will not catch these CPUs that are obviously unstable because you can't do basic things like decompress your video drivers in order to install them, and yet it'll pass the Intel stress test. Part of the instability here, Intel is calling vmin shift. And remember, On Linux, even just the difference between the on-demand performance governor and the performance governor can mean the difference between a CPU that is stable and a CPU that is unstable if your CPU has begun to degrade. The reason for that is because the power governor shifts the voltage the CPU receives because, well, it's based on what the CPU requests, but the CPU knows that it's going to do work. And so the instability actually creeps in the lower end of the voltage ranges. Most of the time, your CPU can be in a low power state if it's not doing anything, 0.7, 0.8 volts. The new 0x129 microcode and later caps the voltage requests at 1.55 volts. And unless you do manual overclocking, then you've got more voltage that's still available to you. So I think Workload, from Workload testing, if you run a Workload as simple as a Minecraft server with a bunch of netcode and bots and all that sort of stuff, on a well-cooled Intel CPU, it's going to cause itself to boost to ruination, at least with the old microcode. Even on conservatively configured W680 motherboards, where we can show that the CPU never actually receives more than 1.55 volts, even measuring it with an oscilloscope at the socket. In my mind, this is because the CPU is requesting boost power, but then can't actually boost. And this is fixed, as far as I can tell, with microcode 0x129. If the CPU could actually boost and do work, it wouldn't degrade. But when it boosts and can't do work, in the case of like a game server, a Minecraft server, where it's like all stalled and weird and bad netcode, you get degradation. So of course, while I was working on this video, Intel published another microcode update, but this should be the final microcode update, and I like the direction that Intel is heading in. They also provided a root cause analysis, and it explains why it has been so difficult for Intel to find, and that is that the degradation starts in the clock tree. This is the hardware mechanism inside the CPU that provides the clock domains for everything inside the CPU, from the cache to the CPU. I mean, obviously not everything inside the CPU is running at 5 gigahertz. There's not even, like, the clock is also fungible, like how much clock time passes here and how much clock time passes here for a finite fixed amount of actual real time in the universe. I mean, everything's relative, I suppose, but it can vary, clock stretching. And so that's really interesting, but the instability creeping in at the low end of the voltage is the instability is in that specific circuit. So we've got our Linux system set up here, and the voltage that the CPU is requesting is only 0.78 volts. This is where the instability first starts showing up. And so if you have somebody that suggests just fixing your voltage, this is papering over instability, physical damage in your CPU, not actually fixing the issue. And this is a problem because the lower voltage gives you thermal headroom to be able to boost. The CPU is designed to boost up to 5.8 gigahertz, and it will be able to boost to 5.8 gigahertz reliably in ideal operating conditions. But we know that there's 2 bugs, at least, with determining what the ideal operating condition is. So check this out. System's idle, 0.78 volts. All I'm going to do is change the performance governor. We're not actually loading the CPU any more than we are. We're boosting now, or we're running with a V-core of 1.27 volts, 1.3 volts, whatever. And this is because the operating system is choosing to keep the cores at a higher state of readiness. They're basically clocked higher, but they're idling. And so it shows that it's spending most of its time running a halt instruction. Well, the E cores are mostly in state C6, but the P cores, the performance cores, are mostly in halt, which is not really a lower power state. I mean, if you really dig into the nuts and bolts of it, halt really does actually save some power, but mostly not a low power state like when we're talking about C states. And this is the part that I was trying to figure out, because all of the overclockers are hyper-focused on this on the Windows side. And in the data center, we don't care. We just want the system to be stable. But we also want to get the performance we paid for, like the boosting up to 5.8 gigahertz. And it turns out that the voltages that the CPU requests is not a hard and fast table. It is actually dependent on a bunch of other variables. Load line, sure, but also the thermals. And so the boosting characteristics when the CPU is under load depend on whether or not this is a tower cooler, whether or not this is an AIO, how rapidly those things are being carried away, and also the specific workload that you're running, because it looked like some workloads were more unstable than others. But since Intel has been able to hone in on this is where the instability is being introduced, I suspect that workload-dependent CPU degradation is no longer going to be a thing, because the workload-dependent aspect of it is related to the thermal properties of the actual boost algorithm, I suspect. We'll know soon enough, But that makes sense with what we're seeing here because, again, the actual work the CPU is doing here is not changing. It's not even really technically boosting because we're not really going over 5.3, 5.4 gigahertz. I mean, we could go to 5.5 on basically every core. So it's still low power-ish, but if we actually had a lightly threaded workload, it would boost up to 5.8 gigahertz. And we would see our V-core boost up to like 1.4, but it's going to stay well below 1.55, even if the motherboard load line stuff is suspect, and now also with Intel's correction to their own thermal algorithm. So there's a lot going on here, but this is sort of the ground truth of what's happening under the hood. And this will also translate into gaming motherboards as well, although with the gaming motherboards having a little bit different variables and different companies pulling different knobs and tunables to try to get better gaming performance, it might be a little bit different, but this is the brass tacks of trying to use these things 24/7 with stability. And this is also why just changing the performance governor in Linux led to more stability. It's like if you just change the performance governor from on-demand to performance, your CPU is going to sit at a higher V-core, but it's requesting it. You haven't hard-coded the V-core, which is going to negatively impact your ability to boost and do anything else. And it's also going to mean that your thermals are perhaps a bit worse because you're probably going to lock it in a little higher than where it locks in here, or you're going to be relegated to like 5.3 gigahertz, which are, again, suboptimal solutions to the problem here. Like the CPU, if you just tell it, hey, be in performance mode, it's going to request 1.3 volts instead of 0.75. What about the 13700T and the 13900T CPUs that I had access to? Ones like these. I mean, remember, Intel says these are 35-watt parts. They can use up to 106 watts, though, before actually backing off in their specs. Because Intel specs actually allow much crappier VRMs for the T-series CPUs specifically. Think small form factor and business-class desktop CPUs. But these CPUs also still experienced failures at an elevated rate, although way less than their i9, desktop counterparts. Interestingly, the failure rate is a little worse than the historical average. Historically, this group of T-series CPUs report that they see about a 1% failure rate in T and low power processors, but the failure rate with these is about 6%. This is still way better than the K-series CPUs, but keep in mind, this is a much smaller population of CPUs that I have to look at. So, bad batch or something like that could also factor in here. Like their high power counterparts, though, the instability creeps in at the minimum end of the voltage range. So just changing the performance governor in Linux from on-demand to performance will make the system stable again, which is weird to experience, but that's reality. Unless your CPU is quite far gone, and then in which case you're going to have to replace your CPU. Low power is also a little misleading here. When we're talking about boosting, a single core boosting on this T-series CPU can still use 60 watts. The power window for these 35-watt parts is actually something like 105 watts in reality. So if you just have one of these cores running full tilt, it can use 60 watts. And again, workload matters. Something like Minecraft is far worse than cryptocurrency mining, at least looking at the population of servers, looking at the power usage history, and looking at all that. So overall, if you use these CPUs, are you safe? If you're a gamer and you want to get more than a year or two out of your system, I would use tools like Hardware Info 64 on Windows to see if it's reporting voltages that are more than 1.55 volts and avoid that entirely. Configure the board for defaults. Make sure your BIOS is updated and running the newest microcode. And Intel has extended the warranty by 2 years. So with all of that in mind, I think basically at this point in 2024, you're probably safe. And looking at message boards online and everything else, it looks like Intel is struggling a little bit to keep up with the RMA demands, as this had been happening for quite a while behind closed doors. Now it's a little more public. Intel has mostly agreed to remediate the situation with large OEM customers too, which is not something that they had before and was a source of great frustration. These T-series CPUs, they're OEM, they're trade. They only have a 1-year warranty. And so Intel was like, I don't know, it must be something you're doing. I don't know. And so, there's also another thing here going on. These day trader folks are sort of swooping in to try to make up stuff about Intel that disfavors Intel. And you have to watch out for that as well, because there's a lot of things that just aren't even connected to reality. At the end of the day, remember, 50% of these CPUs are fine. And with the new microcode and BIOS updates and what the board vendors are doing to raise the minimum voltage, that's going to stabilize at least 15% of the half that are questionable. One of my contacts expects to pull at least 22% of their CPUs, their i9 CPUs, over the next 3 months. So we could be looking at physical CPU replacement upwards of 22%. but it's still better than half. And also, you know, some of the Unreal Engine developers, they were also getting half, roughly, which is encouraging. It's not fabulous, but at least work is being done to get to the bottom of it and make customers whole, which is all I've ever wanted. For multi-core workloads like Cinebench and everything else like that, I don't think there's really any impact there either because Y-Cruncher was always stable. Another thing that bothers me here, though, is that I think Intel is not completely at fault, but perhaps political infighting kept the graybeards at Intel from doing a better job. They need more autonomy to be able to speak up. I mean, nothing is more frustrating than a manager who's smart enough to internalize the knowledge that you're giving them, but they're either too busy or too lazy to put in the effort. And then they also second guess what you say. It's like, which is it? Are you know, if you're going to delegate. Graybeards gave plenty of warning. I've got all kinds of really just juicy stuff that doesn't matter for this video. But Asus in particular, on both the W680 and Z690, Z790, they really did a number on Intel. As far as I can see, they are not sharing in the responsibility to make customers whole, and that isn't right. It's just the voltage those processors were receiving. This is unfortunate. I have no doubt this was obvious to insiders even before 14th Gen dropped, and it took a public meltdown crisis to dislodge the internal political meandering that was going on, and that half of these CPUs have been fine with whatever horrors the motherboard makers have visited upon them shows that Intel does have the potential to deliver CPUs that really can dissipate 325 watts without any issues. Igor's lab did a really great study on CPU voltage requests and vid tables. You should check that out. The vid request shows how much variation there is across CPUs in terms of how much voltage it needs to achieve a certain frequency. That mattered here, much to my surprise. There is great insight in Igor's lab's data, and mining that data from the systems that I had access to, including writing my own utility, check out that video, it shows that CPUs that want more voltage started to develop issues before their other counterparts. So part of the issue here might be hugely variable quality control. And in that case, again, it's up to the graybeards with the tribal knowledge to save Intel. Once again, I hope Intel management wises up and realizes what a tremendous resource they have in their older and more experienced workers, and that Intel can more, sort of closely keep an eye on the graybeards and listen to them. Maybe they needed some designated graybeard whisperers, because those are the folks that you need to be competitive in the global semiconductor landscape. And if you want Intel to have really kick-ass gaming CPUs, those folks at the bleeding edge of the process technology and squeezing every little bit of lightning out of the rock in the foundry, those are the ones that you need at the forefront for doing all of the cool overclock, off-label stuff. And I really would love to see them get a little bit more attention and a little less mistreatment from management based on, again, the stuff that I have. It's been interesting. Wendell, this is Level 1. Let's chat some more, hang out on the forums. I have a feeling this is not the last chapter in this story, but if you were Intel hesitant, I think that most of the reason to be Intel hesitant has passed, but I still don't think that you have any real overclocking headroom beyond what you sort of get out of the box with the defaults here, at least if you don't want your processor to degrade in a year or 2 or 3. But with the extended warranty, that's nice. 15th gen is not far off either, so the future is pretty interesting, I think. I'm Wendell, this is Level 1. Thanks for watching. Let's chat in the forums. I'm signing out, and I'll see you there.